All right, this is an example in the textbook of a set that is not regular, and you can read it in the textbook. But I just wanted to kind of walk through it in sort of a summarized format to explain how it works. So the language in question is this language, which we have seen before. This is the language where it consists of all strings of n zeros followed by n ones, and that could be like just lambda, no zeros followed by no ones, or it could be 0, 1, or it could be 0, 0, 1, 1, or 0, 0, 0, 1, 1, 1, and so on, as long as the number of zeros matches the number of ones. We saw this set before. We actually looked at a phrase structure grammar that could generate this set, which shows that phrase structure grammars can actually define more languages than finite automata can. Although automata are sort of more convenient. So this is not a regular set. We're going to prove it. The proof will basically involve showing that no finite state automaton can recognize this set. It's impossible to make a finite state automaton that will recognize this. And Kleen's theorem said it was an if and only if, right? Kleen's theorem was sets are regular if and only if they are recognized by finite state automata. And the finite aspect of this definition is essential for this proof, okay? Automata have to be finite number of states. So we're going to assume, seeking contradiction, that there exists a machine M with that generates this language. Okay, so L of M is going to equal this set. Okay, so we're assuming actually that it is regular to start with, assuming that there does exist a machine, a finite state automaton that's going to do that. So since M has a finite number of states, we're going to say that that finite number is capital N. So N, the number of states. Well, N is a natural number, so we could, I'm sorry, I made a mistake here. We could have this machine, we could feed it capital N zeros followed by capital N ones, and that would count. That should be in the language, right? So M must recognize 0 to the n, 1 to the n. Now, if it does that, then the result is going to be something like this. We're going to have, we're going to start at our state 0. We're going to receive capital N zeros and then receive capital N ones, and then we will end at some state down here that should be an accepting state, like this. Now, I have labeled these states, and this is the way the textbook does it as well, 0 through 2n. Right? And 2n because this is a string of length 2n, right? It's n plus n. Now, not all of these states are distinct from one another. And we know that actually by the pigeonhole principle. The pigeonhole principle tells us that since there are only capital N states, but here we have 2n states that need to exist, some of these have to be equal to each other. In fact, many of them will actually be equal. But in particular, of the first n states here, of the first n plus 1 states, from 0 to n, that's n plus 1 elements, of those, at least 2 of them have to be the same by pigeonhole principle. So what we're going to do is actually say this string of states that we've made, we're going to take 2 of them, those 2 are the same, and grab those, put them together since they're equal, and pinch this into this, like if this is a rope, pinch it together, forming a loop. That would look like this. So instead of going 0 in a linear fashion all the way to 2n, at some point, I've done it here at state 2, at some point it's going to pinch together and form a loop, where state 2 is the same as state 13 or something like that, and then it'll finish up going all the way to state n. All right, so this is looping together, and then it continues all the way down to state 2n. Now there's probably loops that are going to happen over here too, but it doesn't matter for now. We just have this cycle. Let's say the length of that cycle is t. Right? So now the problem is this machine will also recognize n zeros followed by t zeros followed by n ones. So the reason for that is what you could do is come along here and go around this cycle twice and then finish up. So that would be, if it was just once, we'd get capital N zeros. But if you go around it twice, you get t more zeros in your string. right? And then you've got the n ones. So by going around that particular loop twice, we get this. Now this is 0 n plus t 1 n. In this string, the number of zeros and the number of ones are not equal to each other, which is a problem, because that string is not in the language, thereby contradicting the assumption that this machine generated the language we were trying to get, right? If this machine accepts all of the strings in the language, but it also accepts some strings that are not in the language, then the language generated by this machine is not actually equal to the one we wanted, right? It's bigger than the one we wanted. Contradiction, therefore, no finite state automaton can possibly exist to recognize this set, and therefore this set is not regular. So, one way to this is the proof. This is the proof of the way it's laid out in the book. Another way to basically conceive of this is essentially if you need to have a finite number of states, but you could have arbitrarily large value of lowercase n, right? That arbitrarily many zeros followed by exactly that many ones. In order to keep track of the information of how many zeros there are, the only thing an automaton can do is move to another state, right? That's how it keeps track of information. So if you want to keep track of the fact that you've seen 7 zeros, then you have to have 7 states. And then you would need to go backwards through those 7 states to make sure that the number of ones is going to match exactly the number of zeros, right? So if you wanted to go up to 7, you could do that. But since that number of zeros can be arbitrarily large, you would need an arbitrarily large number of states to keep track of that information so that you can guarantee that you have exactly the same number of ones after your zeros end. So there's no way to do that with a finite number of states. So that explanation that I just gave verbally is a more sort of intuitive way to understand what's going on here. Now, the other thing I wanted to say about this is that it is possible to do this with a phrase structure grammar, like we saw. And one thing I didn't go into is different types of grammars. You can read about that in the textbook if you want. There's a particular type of grammar called a regular grammar that is a grammar that satisfies certain rules. And regular grammars generate exactly the same languages as finite automata. So that grammar that we looked at to generate this set was not regular. So, all right, yeah, that's about it. I know this is just a taste, but I hope this is, this section or this chapter has really given you a little bit of insight into the notion of a theoretical machine and how that models computation. This is all about recognizing languages, which is one of the main topics here. But if you read about Turing machines, you'll find that they can also do things like perform binary addition, or compute, count things, like compute the number of different, like the size of a set, how many elements are there in a given language. They can do a lot of things because they have outputs as well as a yes or no answer at the end, as well as accepting states. So yeah, really, Turing machines do everything that that computers can do and more. So that's where I'll leave it. I will see you in the review week, and then the final exam will be a take-home final we have in the very last week of the semester. So keep your eyes peeled for that review material that I'll be putting out soon.